Start with questions from homework. So I think to this point we've done like up through 20 or so in the homework, 22, something like that. Does anyone have questions yet on anything? Giselle, is that a hand?
Yeah, can you just tell the answer for number 16?
Sure. Get out my book here. (16) is the component form is -514, and the magnitude is 220 or square root of 221, or about 14.9.
Thank you.
You're welcome. Anybody else? Nothing. Okay. Well, I guess let's get this show on the road again. I think where we left off last time, we were talking about vector operations, and we just finished talking about standard unit vectors and linear combination form, correct? Does that sound right to you guys?
Yeah, I think on the top.
Yeah, that was the last thing we were gonna, or the next thing we were gonna start, right? Correct. Okay. So to this point, we had defined vector addition and subtraction and scalar multiplication. Those were our three vector operations to this point. I hold it. Today we're going to define a fourth vector operation called the dot product. So our definition for a dot product is if I have two vectors u and v, the dot product of u and v is going to be the first components of the two vectors multiplied together plus the second components of the two vectors multiplied together. Note that what are we getting back when we do a dot product? What kind of value is this? It's just a real number, not a vector. This is the only vector operation we've encountered so far where what we get back is not a vector, it's just a real number. Or sometimes you'd call that a scalar, right? In vector talk, real numbers are just scalars. So the dot product actually has a lot of application. So let's take a look at some properties that we can use to do the dot product. So the dot product is commutative, meaning that if I take the dot product of u and v and the dot product of v and u, I get the same number. If I take the dot product with the zero vector, I get the number 0, not the vector 0, but the number 0. I can distribute with the dot product either from the left or from the right. If I do scalar multiplication with the dot product, I can do that scalar multiplication any place. I could do it to u, I could do it to v, or I could do the dot product of u and v first and then do the scalar, and at the end. Those all give us the same result. And then if I take the dot product of a vector with itself, we get that that is going to be the same as the magnitude of that vector squared. So I think in the homework, we ask you to prove each of these. Let's prove one of them, just to kind of give you a feel for like how you go about doing this. So let's just do the first one. So we're going to start by just defining two vectors. So I'll define the vectors u and v, or if you don't really like using u and v because the letters look a little bit similar on your paper, you could pick two other letters, a and b or whatever, doesn't matter. They're just names. So I'm going to start just by declaring I have two vectors, u and v, that are, and then their component form u1, u2, v1, v2. So if I do u dot v, that's just going to be u1 times v1 plus u2 times v2, right? Now u1 and v1 are just real numbers, correct? So I know that I can switch the order that I do the real number multiplication, and I could do like v1 first and u1 second. And likewise, I can do the same thing with u2, v2, so I can just switch the order of the multiplication. Why can I do that? Because for real numbers, multiplication is commutative. Everybody agree? Now, if I use my definition of a dot product, what vector is first in my multiplication here? V. So this would be the dot product of v and u, and look what we've done. We've shown that u dot v is equal to v dot u. That's it. So just if we take the big picture here, on all of these proofs, what you're going to do is you're going to start by using the definition of your dot product to turn it into like into just sums and products of real numbers. Use our properties of real numbers to kind of move things around, and then use our dot product property to put it back into vector speak, so you're back to the dot product at the end. Right? That's the general idea. Very much so in like geometry, when you proved like congruence theorems, often what you did is you turned it into equality, used all your properties of equality, and then turned it back into congruence at the end. You guys kind of remember doing that? Very similar pattern here. Okay? So I think we see that in the homework where we ask you to prove these ones. We've already did one of them. Yay! All right, let's do a numeric example to just make sure we got the feel for this. All right, so we have the vectors u and v and the vector w. Use the definition of dot products and the above properties to solve the following. So if I look at my three vectors I'm given, w looks weird, right? What's it called when I write a vector like w in that way? What's that form of that called? Where it's got the i's and j's in it? It's not the standard form. Giselle? That was called linear combination form. So the first thing that I would want to do before I do anything else is I want to take that linear combination form and rewrite it into component form, so that when I use my dot product definition, if I look back at that, my vectors were in component form for that. So that's what I would want to do first. So how do I rewrite 8i plus 4j in component form? Well, the coefficient on the I is just going to be my x component, and the coefficient on my j is just going to be the y component. So it's very easy to go back and forth between linear combination form and component form. Very simple, but you got to remember what they are and what it means, right? Which is not trivial because you got a bunch of stuff thrown at you last time. All right. So if I want to do u dot v, well, that's just going to be the x component of u times the x component of v plus the x or the y component of u times the y component of v. Or negative 17. That feel okay to everybody? W dot v. Well, it's going to be the x component of w times the x component of v plus the y component of w times the y component of v. Everybody feel so far so good? So next one we have 5w plus, or 5w dot u. So here I could use one of my properties of dot products, and I would probably do that here, me personally, is I would use the scalar associative property, and I would think about it this way, where I'm going to do the dot product and then multiply it by 5. Now, you don't have to do it that way. You could do the 5 times w and then do the dot product, or 5 times u and then do the dot product. Either is going to be fine. So I'm going to have 5 times, and then the x component from w times the x component from u plus the y component from w times the y component from u. So that's going to be 5 times 16 plus negative 12, or 20. So my last one here is u minus w dot 2v. Now, I could, if I wanted to, do the distributive property and distribute that dot 2v to both vectors. But that means I'm doing 2 dot products instead of just 1 dot product. I'd rather just subtract u and w. And then I'll do the multiply the 2 into the v. Maybe I should write it that way. And now I'll just do my dot product. So 12 plus negative 70 is negative 58. Is everybody okay with what I did there? Again, fairly straightforward, right? Just another operation, pretty easy operation to use, but you have to remember the definition. So let's look at some applications for things we can do using dot products. So let's say we want the angle between two vectors. So let's say we have some vector u and some vector v, and we're looking to find the angle between these two vectors. Everybody's okay with that? Now, what does this kind of setup look like to you? I see that it's a side and another side and an angle. Looks like a side angle side kind of situation. We're going to be solving for a triangle, right? The question is, what is the triangle that I'm going to be doing? So the triangle I'm going to make, I'm going to add in this side. The question is, what should I call that side? Well, the way I've set this up, it should be u plus something should equal v, right? Because we're head to tail, so that means we're adding the two things together, and the head to head means that's what's going to equal. Everybody's okay with that? So what does that spot have to be? Well, it just has to be v minus u. Sounds good to you guys? So far, so good? All right. So if I use the law of cosines, I can say that the length of the side u minus or v minus u squared is equal to the length of the side u squared plus the length of vector v squared minus 2 times the length of vector u times the length of vector v times cosine theta. Everybody so far so good? Okay. I want to go back and remind you guys of this property 5 for vectors. It says the magnitude of the vector squared is equal to the dot product of the vector with itself. I'm going to use that property kind of going in this direction. On this first piece. Everybody feel okay there? I'm now going to use the distributive property of dot products to FOIL out that dot product. Everybody's okay there? So I have v dot v and u dot u. I'm going to use that magnitude, that property 5 of dot products again, to rewrite that as the magnitude of v squared. And then the magnitude of u squared. Oops, squared. And if I subtract the magnitude of v squared from both sides and the magnitude of u squared from both sides, I have that. And we'll divide both sides by -2 times magnitude u times magnitude v. So the -2's can cancel out. So I can write that cosine theta is equal to u dot v over the magnitude of u times the magnitude of v. I want to point out to you that the dot in the top is dot product. The dot in the bottom is multiplication. How can I tell the difference? From context. In the top, I have vector and vector with the dot between them. If you have a dot between two vectors, that's a dot product. In the bottom, I have the magnitude of u, which is a real number, and the magnitude of v, which is a real number. A dot between two real numbers is multiplication, right? So just be very careful with this formula. The numerator is a dot product. The denominator is multiplication. So let's go ahead and kind of formalize this. So given two non-zero vectors, u and v, in standard position, the angle theta between the vectors can be found by the formula that we just developed. Or if you'd prefer the theta by itself, you can do the cosine inverse to both sides. Now keep in mind, the output for cosine inverse is 0 to 180, right? Is that okay? Can I have an angle bigger than 180 between two vectors? No, right? Like, even if you were saying like, ooh, that one. But we never talk about the angle between two things going that way, do we? Never did we do that in geometry. So yeah, of course, the angle between two vectors should always be something between 0 and 180. So good, no adjustment needed. Wonderful. Wonderful. Let's do an example where we'll do that numerically, just to show to ourselves that this is not as bad as that derivation was. The calculation itself is not so bad. So let's say we want to find the angle between the vector 7, negative 6 and the vector 2, 2. So there's three things I need for this calculation. I need to do u dot v. I'm going to need the magnitude of u and then the magnitude of v. So I'm just going to list these three things kind of separately and then kind of put it all together in the formula at the end. So the dot product is 2. How do I do the magnitude? Do you guys remember? Square root of x squared plus y squared. 49 plus 36 is 85, I think. And then the magnitude of v, square root of 2 squared plus 2 squared is equal to square root of 8. Now, I know I can simplify that radical, but why do I care to do that? I wouldn't, because I'm just plugging it into cosine inverse anyways. So like if I'm not presenting as a final answer, why would I worry about rationalizing or reducing a radical or rationalizing a denominator? I wouldn't do any of those things, right? Because I'm just about ready to plug this into my calculator anyhow. Oh yeah, of course. We're just doing that. So cosine inverse. And I'm going to use the fraction command here, because if I don't, I'm going to have to use like kind of a lot of parentheses, and it'll get a little confusing. So I would strongly encourage you on this to make sure you're using that fraction command. Yes, sir. Of course. And I get about 85.6, assuming that my calculator was in degree mode. What's the best way to check this? I mean, I would just sketch a picture and see if the angle between it looks like it's about 85, right? So if I do 7 over and then 6 down, let's say 3, so do that. And then 2 over and 2 up. How's that angle look to you guys? Looks pretty 90-ish, which is awful close to 85.6. I'm pretty happy with what I did there, right? I know at least I'm in the ballpark, then I'm not like way out in left field wrong on that. Now, is that a perfect check? No. But like, is it probably good enough for most of this stuff? Yeah. This is as good as anything else. Just does this even make sense? Is that a reasonable angle to get? Sure, it looks pretty reasonable. And it was quick, right? I didn't have to do much other than draw a little picture. Okay. So there's a special situation that we'll often be interested in. And that's where the angle between two vectors is 90 degrees. We call that situation, or we call two such vectors orthogonal, is the word we use when the angle between two vectors is 90 degrees. Let's check, or let's kind of think about how we could check to see if two vectors are orthogonal. So let's say that theta is the angle between two vectors, and that's 90 degrees. Remind me again, what's cosine of 90? First semester, people? It's not 1 because it's the x-coordinate. It's 0. Sine of 90 is 1. Remember, because that's straight up and down. Good. And so if I know this should equal u dot v over magnitude u times magnitude v, right? Because that's what cosine theta is equal to. So I have this fraction that's equal to 0, right? When is a fraction equal to 0? Only when the numerator is equal to 0, right? So we can say then that formally the two vectors are orthogonal if and only if their dot product is 0. Which is lovely, right? So if I know the two vectors are orthogonal already, I immediately know their dot product is 0. Or if I find their dot product to equal 0, I know that those two vectors are orthogonal. Let's do a numeric example just to kind of play with that idea. So if I want to show that these two vectors are orthogonal, what does that mean I'm going to do? Yeah, I'm going to do the dot product, and what answer should I be getting? Should be getting 0. Negative 80 plus positive 80 is 0. Done. That's all. Oof! Mr. Cool looks so easy. Right? Isn't that lovely? Really is. Okay. That's gonna be the last thing in eight two. In 8.3, we're going to look at some real-world applications for vectors. So this means they're going to be story problems. So no new content is really happening here. We're just going to kind of see some story problems where we can apply some of these ideas. So one situation is one that we are already quite familiar with because we did a bunch of problems like this first semester. They've just returned, and that we can use them now in a new language, right? So it says a boat leaves a port and averages 40 knots, traveling for 2 hours on a course of 215 degrees. Then the boat turns to a bearing of 162 degrees and travels at 55 knots for 3 hours. What is the distance and bearing of the boat relative to its starting position at the port? So I'm going to start just by figuring out the magnitude and direction for the boat vector. Well, the boat is traveling 40 knots for 2 hours, so that means it went. The length of that trip was 80 nautical miles. If it says a course of 215 degrees, that's a bearing. What's the difference between a bearing and a standard position angle? Was there a difference? Yeah. The bearing starts from due north and it goes clockwise, right? So, oops, give me a color here. So my bearing was 90, 180, and then like 35 more. So if I want the standard position angle, 90, 90, and the other half of that is 55. So my angle there would be 235 degrees. Everybody's okay with that? I shouldn't have called this boat because it was just all boat, right? So I'll call it F for first. How's that? We'll call S for second, the second thing it does. Is that okay with you guys? Just a name, it doesn't really matter. 55 for 3 hours. So that had length 165. And again, it says the bearing is 162. So we need to convert that into a standard position. So we do 90 and then 72 more. And then to get the standard position, that's 90, 90, 90, and then 18 more. So that's going to be 288. I'm now going to resolve those two from magnitudes and directions into standard or into component form. Notice this is still looks the same as what we did before, right? It's just now using the language of vectors. So I'm using like this wedge notations and all that. So when I type those into my calculator. Actually, I don't even need to type those in my calculator. It'd be fine to just do it later. So then my total, the result for, maybe I'll use R for resultant. Yeah. It's just going to be vector F plus vector S. So that's going to be 80 cosine 235 plus 165 cosine, not sine, cosine 288. So that's 510. And then I do the same thing, but instead I'll do sines. So that gives me the 510 negative 22246. So the last thing I would need is the magnitude of that resultant. So to calculate the magnitude of the vector, I just do x squared plus y squared, square rooted. And then here I have to be a little bit careful with the negative. If I'm going to just do that, I'm going to put in parentheses. So 22251. And then if I want the direction, draw my picture. So 510 over and 222 down is going to be like that. So that's my standard position angle. That should be 360 minus that leftovers that I call phi. And I always calculate phi the same way, by doing the tan inverse of the absolute value of the y over x, rather than typing all those numbers, and I just wrote it that way. Is everybody okay with that? Since I'm just going to use my go right to my calculator to do that. 360 minus tan inverse. And then I guess I will do the absolute value because I have those stupid negative signs rattling around. So math and then over to number. First option is the absolute value. I'll put my fraction here. So it's going to be y over x. I didn't. Too dumb to figure out what I wanted it to do. Guess I'm just going to have to approximate this one. Oh well. If I really wanted to, I could store it, but 271.31. And if you wanted that as a bearing, then you could do that, but let's just not, right? What do you guys think? Sound good? Yeah, whatever. Okay. Questions on what we did there? Same thing that we did before, right? We just have names for these things that we're doing now, which is lovely. I love names. It makes it easier to talk about stuff. Like, hey, who's that person over there? It's going to be easier to be like, yeah, that's Giselle, right? Like, it's way easier than like, hey, you. Way back before I started here, there was a math teacher who the running joke was like, didn't know any student's name, so he called everybody kid. Like, hey, kid. Or, yeah, kid, what do you need? And somebody made him a pretend seating chart, and in every desk it just said kid, 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 kid. So, anyway, that's a funny joke. All right. So, next thing is we have this new idea. So what I want to do is, let's say we have some vector u. Bloop. Or actually, let's just do it like that. And let's say that I want to break that vector u down into the sum of like two other vectors. But I don't want any old vectors. I want it so that those two vectors are orthogonal. So I want to be able to do that. So if we have something silly or something simple, let's say just like use the vector 3, 4. Well, Mr. Kulik, can't I just do like, V could be that, and then W could be that? Haven't we done this already? Isn't this just linear combination form? Yes, that's true. But let's say this time that I have some vector u, and then I have some other vector v, v, and let's say that vector v has like a non-horizontal or non-vertical direction, right, where it's just not one of those, or not a scale factor of one of our standard unit vectors. Then what I want to be able to do is I want to be able to find some vector that's in the same direction as v, that's perpendicular to v, and that still adds up to give me u. This vector that I've drawn in blue has a special name. We're going to call it the projection of u onto v. So that's how we read that symbol, as P-R-O-J, and the subscript is v, or the vector v, and the argument is the vector u. So how do we do this, right? How do we do this? Well, if I can find this vector here, the projection, this is pretty trivial to find W, right? Since I know that the projection plus W has to equal U. U is my starting value. I know U already. So W just has to be U minus the projection, right? The question is, how do I get that projection? Well, we're not going to derive that, but I will give you this. So this is a formula that we can use to calculate that projection. So the projection of U onto V is the dot product of U and V divided by the magnitude of V squared. That's all a scalar now, right? Since the dot product is a real number, the magnitude's a real number. So that's a scalar on the bottom times V. So all it's doing is it's taking vector V and like shortening it down or lengthening it out so that it'll be that perpendicular or part of a perpendicular component that I can add to get U. Go away. Go away. Why are we doing this? How do I get rid of there? Be gone. All right. Two things worth noting about this formula. Oh boy, that's not at all where those were supposed to go. So two things to think, or two things to remember. If we think about the picture I've just drawn, this doesn't really depend on the length of V, right? Because when we build our projection, the length is going to be, all we really care about is it's going in the same direction as V, right? So in a sense, the value for the magnitude of V doesn't really matter. If we are not given that value inside of our problem, what we're going to do is just assume that the length of the vector is 1, that we're just working with a unit vector, and it'll actually make all of our calculations a lot easier. We'll see that in a couple of minutes when we do some examples. And then, as I mentioned earlier, that this quantity, U dot V over the magnitude of V squared, is just a scalar. That's a real number divided by another real number. So this is just scalar multiplication is all this projection is talking about. All right. So let's do some calculations just to kind of cement this process, and then we'll talk about how I can use it as an application to solve some real life stuff. All right. So here it says, find the projection of U onto V. Express U as the sum of two orthogonal vectors, one of which is the projection of V onto U. So I'm going to start with my projection formula. So to do that, I'm going to need the dot product of u and v. So that's going to be 14. And then I need the magnitude of v squared. Now keep in mind that when I square a magnitude, I'm just going to be canceling out the square roots. That's just like 6 squared plus 4 squared. Now, before I go and do this, I'm going to reduce that fraction, right? So let's do that. And then I'm just going to do the scalar multiplication. So 7 over 26 times 6 is going to be 21 over 13. I reduced as I multiplied there. And then that's going to be negative 14 over 13. Again, I reduced as I multiplied. Everybody's okay with that? You trust me that I did that right? I think I did. Okay. So then to get, that's one of the two vectors, right? So that's one of my vectors that I need. To get my other vector, I'm going to call W. I'm going to remember that that is U minus the projection of V onto U. So 3,1 minus 21 over 13, comma, negative 14 over 13. So to do that, I'm going to need to make a common denominator. So I get this is going to be 18 over 13, comma, 27 over 13. So in the end, I can say that U is going to be 21 over 13, comma, negative 14 over 13, plus 18 over 13, comma, 27 over 13. And if I wanted to check, 21 plus 18 is 39, divided by 13 is 3. And negative 14 plus 27 is 13. 13 over 13 is 1. So I am quite confident that I've done that correctly. Is everybody okay with that calculation? How I did that projection? Okay. Oops. All right. Now let's look at an actual application. Who cares about this stupid vector projection? What is this going to allow me to do, Mr. Kulik? Well, how many of you guys are in or have taken physics? Handful of us, great. How's this problem sound? Kyle is going sledding on a hill with a 25-degree angle of incline. If Kyle and the sled weigh a total of 165 pounds, what amount of force is sliding down the hill? Does this sound like a familiar physics kind of problem? If you remember from physics, this is kind of a hassle whenever you're dealing with like a force going applied up or down a hill. I'm going to show you how to do this using vectors, in which every problem is ostensibly the same problem. So there's no like, oh, you rotate the axis and you do like, none of that mumbo jumbo are we going to do. We're going to do it all with vectors and projections, and we'll actually find a shortcut for problems like this that are going to make life even easier than maybe we thought initially. So I'm going to start by drawing a picture. So I'm going to start by drawing my hill. So it's sledding with a 25-degree angle of incline. So if I'm going to draw my hill, I need it to have 25-degree angle of incline. Means that like that angle is 25 degrees, right? Everybody agree with that? I know from the alternate interior angles theorem from geometry, that means that this angle is also 25 degrees. Which means that the standard position for this vector that I'll call h for hill, that the direction for that standard position angle is going to be 360 minus 25, or 335. Everybody's okay with that? Now it says Kyle and his sled weigh a total of 165 pounds. The force acting on that is going to be gravity. Everybody agree with that? So I'll call that force G. Notice G is pointing directly down. So the x-coordinate is 0. The y-coordinate is negative. And pounds are a measure of force, so we'll just call it negative 165. And what we're looking for now is projecting G onto H. And then we're going to need the magnitude of that, because it's how much force. So we're going to project that gravity vector onto the hill, and then take the magnitude of it to figure out the quantity of force. Everybody's okay with what I've done there? But the question is, what is H? What's that vector H going to be? I know it's direction, 335, but I wasn't told anything about its magnitude. What are we going to do? Well, we talked about that. If we're not told what the length of vector v was, we can just assume vector v to have length 1. So if we do that, then we have 1 times cosine 335, and then 1 times sine 335. So H will just be a unit vector. Okay. So now I have everything I need. So the projection of V onto H, or G onto H, is going to be G dot H divided by the magnitude of H squared. So that's going to be 0 plus, well, I'll write it, I guess. 0 times cosine 335 plus negative 165 times sine 335. And the magnitude of H is just 1. Oops, forgot times V on that. Except it's not V, it's H. Okay, so let's just see what this number is real quick. So that's 6973. So I'm going to multiply that by cosine 335. And then I'm going to take that number and multiply it by sine 335. So that's my projection. And then to answer the question, I need the magnitude of that projection, which is the square root of that which is 6973. Wait a minute. We saw that number somewhere before, right? Where did that number pop up earlier? That was just the dot product of G and H, wasn't it? Wait a minute, Mr. Kulik. Are you telling me that I can just skip all that mumbo jumbo and just do the dot product of those two vectors and I don't have to do all that rest of that crapola you just did there? My answer to you is sometimes. And we'll tell you when you can get away with not having to do all that mumbo jumbo next time. So stay tuned. You guys should be able to do up to 50 now. So what are we at? 23 to 50. Those story problems at the end you may want to hold off on to until next time when you get the, like, when can we do the shortcut explanation. Remind me on that we still have to finish that up. Oh, I still have some more to do here. That's good. Okay, so that's perfect. Okay. And we'll see you guys on Wednesday.
So this the